Hi students. So today we are going to begin one more optimization tutorial, and today we are going to look at gradient descent method and how it is often used in machine learning. So till now we have been using gradient descent and the conjugate gradient methods in optimization, and of course you may have heard that as far as machine learning is concerned, gradient descent is very important there also. So I'll look at some of the key differences between the way these methods are used in optimization and in machine learning. I'm Dr. Ganguly. So in today's tutorial, we are going to look at the gradient methods, for example, steepest descent. This is of course the classical method which is used in machine learning. And we are also going to look at two conjugate gradient methods, one new and one relatively classical. And then we are going to compare all these methods in terms of performance in the way machine learning uses these methods. I'm also going to introduce you to something known as the learning rate and how this is related to classical optimization. And also we are going to talk about why gradient descent or steepest descent is actually so good in machine learning and why it is frequently not used in optimization. So this is something which is very interesting. We are going to use Python code to figure out some of these things and guide us and use it as an example. And of course, make it a point to look at tutorial 19 for gradient based method review for the different conjugate gradient methods and steepest descent. And also, of course, you know that if we are using any direct search method in the design space, then the algorithm is xk plus 1 equals xk plus alpha k dk. Now here dk is the search direction and alpha k is the step size. So now let's look at the gradient descent algorithm. So as far as optimization is concerned, what happens is that you start with some value x0 which is given. This is the vector of design variables, sometimes known as the design vector. And of course we have the search direction dk given as negative ck, where ck is the gradient vector. So all you do in the gradient descent method is that you move in the negative direction of the gradient vector, and then you move in the design space using this formula here. Xk plus 1 is xk plus alpha k dk. Now what happens is machine learning is that you actually make this alpha k as simply alpha. So instead of changing this value at each point at each k, you have a typical value here which is kept constant in most cases, or it may be changed using some different algorithm out there. Now in machine learning they use a different symbol. Most of the time it is the Greek letter given as eta, and that's something which is just in terms of nomenclature. It's actually the same as the step size, but it is something which is frequently used in machine learning. So in many machine learning books you will see this formula used, which I have given in blue. That is xk plus 1 is xk negative into this factor, the learning rate, multiplied by the gradient vector. So this is the algorithm which is very often considered to be the gradient descent algorithm. And what happens is that you will find in most machine learning books they will say that the learning rate has to be chosen appropriately. If it's too small, convergence is going to be very slow. If it's too large, then you are going to get divergence of the algorithm. So what happens when we use the conjugate gradient method? So for example, let us look at the case when k is 0. In that case, you have to use d0 is minus c0, which is the steepest descent search direction. But once you have the case where you are beyond k is 0, then you can use the formula given here. So dk is minus ck plus beta k dk minus 1. This is the general formula for all the conjugate gradient methods. So what happens here is that you have the previous search direction dk minus 1, and this is multiplied by this factor beta k, for which different people have propounded different formulas out there. So you have heard of the formulas such as Fletcher-Reeves and so on. And generally what will happen is that then we will move in the design space using this formula. Xk plus 1 is xk plus alpha k dk, where alpha k is the one-dimensional step size, and for each value of k you will typically call some algorithm, a 1D algorithm, and calculate this alpha k. Now if we want to use conjugate gradient in the machine learning approach, then what we will do is that we can just put alpha here, and this will essentially become the learning rate of this algorithm. And what will happen then is that this alpha has to be selected based on some kind of different thinking. Now, why do we not calculate alpha k at each step in machine learning? One of the reasons is you want to be very efficient. And in machine learning, typically what happens is that people are looking to move in a search direction and simply decrease the function. And we will see that actually steepest descent works out quite well if you use different values of alpha. So we will look at that. So we are going to look at two conjugate gradient methods today. One of them is a classical method propounded by Fletcher-Reeves. By classical, we can see it's in 1964, so it's quite old. And we can see here that beta k is given as the norm of ck square divided by the norm of ck minus 1 square. So this is the Fletcher-Reeves method. One of the advantages of this method is that beta k here is always a positive value. So that's something which is useful, and probably this is one of the simplest formulas you can come up with as far as conjugate gradient methods are concerned. But conjugate gradients is not a frozen topic. There are many people who have worked on it. So one of the newer methods is propounded by Dai and Yuan. And this method, published in the Siam Journal of Optimization, is in 1999. So this is relatively new. And in this method, this particular formula given as beta k here is proposed: ck transpose into ck, tk minus 1 transpose into ck minus 1. So of course this can be calculated in a very simple manner. One of the things in many of these formulas which were proposed later is that you have to create a condition that beta k is set to 0 in case beta k value as given by this formula becomes negative. So that has been suggested by various researchers. So now with that background, let us come to the question which will help us build our knowledge about how this method is used in machine learning. So the question is to write a Python program for two conjugate gradient methods which we discussed before, and the gradient descent method, and we have to use the value alpha as 0.1, 0.3 and 0.5 to check convergence. And also we need to look at the angle between dk and dk minus 1. Remember, these are the search direction at the k and k minus 1th point for these methods. Now this particular angle is going to reveal to us certain aspects as to why the steepest descent method works well in machine learning. And we are going to use the same function which we have used many times before, that is x1 square plus 2x2 square plus e to the power minus x1 minus x2, and we are going to start with the 0.5 minus 5, so that's x0. Now let us just review this function. We have looked at it in detail in optimization tutorial 3, but what you can do is that you can take the gradient of this function and set it to 0, and then you can obtain the exact solution. So what happens is that the exact solution comes in terms of the Lambert W function. So using the Lambert W function, we can get the solution as x1 is 0.31277 and x2 is 0.15638. x2 is 1/3 w 3 by 4, where w is the Lambert W function. So I can write x star as a vector given here. So you can see that this is the minimum point of this function here. So we know this exact solution. Now the Lambert W function, for those of you who don't know, is a function which, when it works on some expression a e to the power a, gives us a. So this is the definition of the Lambert W function, and many programs out there, including in Python, they have built-in ways to calculate the Lambert W function. So you can think of this as a different special function, just like we have Bessel function, we have gamma function, we have the Lambert W function. Now look at optimization tutorial 3 for more about some of these aspects. Now we are going to use this fact that we know x star to actually calculate how close we are to convergence. So instead of tracking the norm of the gradient vector, what I'm going to do is I'm going to track the absolute value of fx at any point minus fx star, where x star is given by this value here. Now let us start looking at the different functions we are going to use in the Python code. So the first is the function given as fx, which simply returns to me the mathematical function f of x given here. So this is x1 square plus 2x2 square plus e to the power minus x1 minus x2. Remember, in Python the vectors start from 0, so x0 corresponds to x1 here and x1 corresponds to x2, and this term is e to the power minus x1 minus x2. We have to use numpy here because to use the exponential function .exp I have to bring in numpy. Similarly, we have the function grad fx, and here I return the gradient vector corresponding to this function. So again, by taking the partial derivatives of f of x with respect to x1 and x2, I can get the c vector, and I can essentially hard code it here, and I return this using the grad f function. So in the main program, I have got to bring in numpy as np. Remember, numpy is being used in many places. I import math also. We will use math at some places. And because I'm going to use the Lambert W function, I essentially import Lambert W from scipy.special. And what I do is I set the x2 is Lambert W 3 by 4 by 3, and x1 is twice of x2, and then I can calculate f star is f at x1 x2. So this is certainly going to give me the function value at the optimal point. Now the next thing I do is I define the starting point, that is 5 minus 5. I set a max value of 10. So I'm going to use the for loop of size 10, and I'm fixing alpha at 0.3 here. That's the learning rate or the one-dimensional search, which is actually a fixed number here. We are not going to call any one-dimensional search here. We can think of this alpha now as a learning rate. Now I call the function steepest, and I then call the function conjugate with the Fletcher-Reeves method and the Dai-Yuan method. And in these functions I am passing in x0, max, alpha, and also the value of f star, which is the function value at the optimal point. So now I have the function conjugate, and in this function conjugate I have the for loop here, and within the for loop what I do is I first start with defining the vector c using the gradient function. So c is the gradient vector, and then if I is 0 I am going to say the search direction is negative c, or I'm going to call this particular function here and bring in the search direction from there. And this function d method, it's going to take in the method, it's going to take in c old and d old, and it's going to return to me this vector dk is minus ck plus beta k dk minus 1. So all this logic is going to be done inside this function d method. Now whenever I is greater than 0, I calculate some values here and I print out x. I print out theta, which is actually the angle between d and d old, that is the current value of d, the search direction, and d old, which is the previous search direction. This is basically dk, this is dk minus 1, and I also print out this value here, which is actually the absolute value of fx minus f star, and I print it out to 8 decimal places. So I am using the round function to get that. So this is going to help me track the convergence of the method. As this tends to 0, we can say the method is converging. Now as far as this theta is concerned, I can take two vectors and I can find out the angle between these two vectors. So to do that I use the definition of the scalar product here, and the scalar product definition can be used to give me cos theta between two vectors u and v is essentially u dot v divided by norm u norm v. So then what I do is that I have this simple function here theta. It takes two vectors d old. It calculates the numerator as the dot product, the denominator as the term which is the norm multiplied by the second norm here. So you have the norm d into the norm of d old, and then I basically get cos theta as this numerator by denominator, and then finally I return a rounded value in terms of degrees of the arc cos of this particular value. So since this is cos theta, I have to take a cos here, and this is going to return to me the angle in degrees up to 2 decimal places. Now here I am bringing in the math method, so I have to bring in math in the main function. Now as far as the functions are involved which give me the search direction, I have this function for Fletcher-Reeves and this is for the Dai-Yuan method. And you can of course clearly see here that the formula for Fletcher-Reeves is given here. So that's what I'm calculating here, the dot product of C and C here and the dot product of C old and C old. Remember, the CK is C and CK minus 1 is C old, and then I finally return minus C plus beta into D old, which is this formula here. Now in the Dai-Yuan method, I calculate beta as given by this function here. So on the numerator, you have the dot product of C and C, and in the denominator, you have the dot product of the D old value, dk minus 1, and C minus C old. And here I put in one more piece of logic here, that if beta is less than 0, beta is set to 0, and then I return minus C plus beta into D old, which is based on this formula here. Now of course I have this methods function here which takes in the method, and if it is Fletcher-Reeve, I call the Fletcher-Reeve function. If it is Dai-Yuan, I call the Dai-Yuan function. If it's neither of these two, it is something else. I basically say invalid method, because this simple program I have, it only works for these two methods. Now let's take a look at the steepest descent function. This is very simple. So here all I have to do is calculate the gradient vector, put it in C, and then I say D is minus C, and then I essentially print out the value of X. I print out the value of theta between dk and dk minus 1, and I print out the absolute value of the difference between fx and fx star. And then I use the fact that x is x plus alpha into d, which is this formula here. Xk plus 1 is xk plus alpha k dk. Now the important thing here is that I'm not using alpha k here. I'm simply using alpha because I'm using alpha as a learning rate. So now let us look at these cases, and what we are going to do is we are going to change the value of alpha as 0.1, 0.3 and 0.5 and see how these methods do. So of course in the main program what I am doing is I am calculating all these values, and then I am invoking the steepest function, the conjugate function for Fletcher-Reeves, and the conjugate function for Dai-Yuan. And remember, the optimal value is known to me as this value 0.31277 and 0.15638, and alpha is 0.1 is coded in here. So that's something to keep in mind. Let's look at what happens with steepest descent and Fletcher-Reeves. So you can of course see that it's converging slowly, and very interestingly the steepest descent is pretty slow in converging here. It is quite far from any optimal point at this point. Now the Fletcher-Reeves does converge to a point which is pretty near the optimal point. So at least in this case Fletcher-Reeves is converging much better. Now remember, here I'm not using anything like an exact line search. So I do not get theta is 90 degrees. And this is one of the powerful things which is done when you use machine learning. Machine learning people do not actually use the exact step size calculation in steepest descent. So they do not get that 90-degree problem and the zigzagging which is present in this method, which we have fixed using conjugate gradient. Since they are simply taking a value of alpha or learning rate and just running the algorithm, they get some particular values here, and you can see of course the function is getting close to the optimal point, but it's nowhere very close, at least at this point. It may converge after some time, that may take place, but I have used a max value of 10, so that's what I'm showing to you here. What happens to Dai-Yuan? Now this is very interesting. The Dai-Yuan method actually converges quite well, better than Fletcher-Reeves I think in this case, and you can see this result here. The value has come to 3.144 e to the power minus 5. That's the difference between f of x and the f star value, and the optimal is pretty close to this actual optimal here. Steepest descent is not doing so well here. Let us now increase the alpha value to 0.3 and see what happens with the results here. So all I have done in this code, the main function, is I have changed alpha to 0.3. Same thing here, calling steepest, calling conjugate with Fletcher-Reeves, calling conjugate with Dai-Yuan. Now you see with point 0.3 the convergence of the steepest descent or the gradient descent is much better. So now we are using a learning rate of 0.3 and you can see you have converged pretty well and pretty rapidly here. So this has become e to the power minus 7 here, and the optimal point is actually pretty close to the true optimal point. Very interesting result. So with this learning rate of 0.3 also we are nowhere near 90 degrees. So in fact this is an advantage here because by not using the optimal learning rate you are doing better in this case. Now if you go and look at my steepest descent method lecture, you will see that the fact that theta is 90 degrees happens because if the line search criteria is satisfied, then you get the point that dk dot dk minus 1 is going to be 0. So that is the condition which actually mandates that you have orthogonal search direction. The fact that in machine learning you are not using the line search criteria to get alpha means that you do not basically have to specify that condition, and that is actually working out better here as far as steepest descent is concerned. It's in fact doing better than Fletcher-Reeves. If you see the results for Fletcher-Reeves, you have of course converged near the optimal point, but still it is further than steepest descent. So in fact in this particular case you can see that steepest descent is actually doing better than Fletcher-Reeves. Now that doesn't mean we should give up on conjugate gradient methods completely for machine learning problems, because in this problem you see steepest descent has converged, but the Dai-Yuan has converged even better. So if the Dai-Yuan method is seen here, it's actually converged almost exactly to the optimal point in just a small number of steps. And you can see this is 0.15638, 0.15635 here. Pretty good convergence, and the norm also, or the absolute value of fx minus f star, is very small here. So till 8 decimal places it's basically 0. Now let's look at a case which may be somewhat disturbing to some of you, but that's part of the problem about not doing a one-dimensional search. Let us increase the value to alpha is 0.5 here and again run the code. The same main program, all we have done is changed alpha to 0.5. And now you can see the steepest descent is actually diverging. So you can clearly see these problems here in terms of the not a number and very large numbers which start coming. So this is clearly an example of when a code or when an algorithm diverges. So this is the situation which happens when alpha value is too large. So one of the challenges in picking the learning rate for machine learning is to choose an appropriate value. In this problem, we saw that 0.3 was a pretty appropriate value, which was working very well. And in the case alpha is 0.5, both the steepest descent and the Fletcher-Reeves are actually diverging. So this is something which can happen every now and then. But very interestingly, and I was rather surprised to see that the Dai-Yuan is actually converging for alpha is 0.5, and this is a very interesting result which actually tells you that there may be some possibility in terms of research about looking at conjugate gradient methods for machine learning, and certainly the Dai-Yuan method looks good here and you can see that. So for a homework project, what you can do is that you can not only look at what I have done, but also look at the different conjugate methods which we have studied previously in our previous lectures, and then look at different learning rates such as 0.01 and all the way to 0.7 and see what happens. And instead of stopping at just a maximum iteration of 10, which I have used here because I wanted to fit all that data within the slides, you can go up to 50 for example and see how things go, and you can build in some safeguards in your code to make sure that if you are diverging then you basically stop the algorithm so that you do not get those things which are going on in the code I showed, for example the NaN values, the values where the numbers are becoming too large and so on. And then after that you can write your comments on the comment section of this video and see what you have learned from this particular process. So to conclude today's lecture, what I thought I would do is I took a slight detour from optimization into machine learning. Now, very often people will tell you that optimization is very critical in machine learning. Now, that is true, but the way machine learning people are using optimization is slightly different. Instead of using the step size, they use the concept of learning rate. And because they use the concept of learning rate and they use gradient descent, the algorithm typically has this form here given by the equation in green. That is xk plus 1 is xk plus alpha dk. So we see we have dropped the k subscript from alpha, which means that alpha is actually just a number here. We are not doing a one-dimensional search using golden section or any method and then getting a very exact number here, but we are simply using some value. And this is something which is often done in most machine learning situations. There are of course various methods to slowly change this value of learning rate as the k builds up, and there is a lot of literature out there on these kind of methods. Now, one of the reasons gradient descent works well in machine learning is that the search directions are not normal. So dk dot dk plus 1 is not 0 because alpha is not something which is going to satisfy the line search criteria because it is not based on an exact line search criteria. Now, one of the problems with conjugate gradient methods is they do need a good step size selection. But interestingly, we found that some of the conjugate gradient methods seem to be doing relatively well with even this kind of step size selection, which is based on a learning rate concept, particularly the Dai-Yuan method and even the Fletcher-Reeves method in some cases. So it may be worthwhile to investigate if the conjugate gradient methods actually do reasonably well for these kind of problem. Now, now one of the things you can see is that there's a difference in approach between how these methods came up. The optimization methods have come up through mathematics, and so you will find that very often the preciseness and the closed form solutions following the gradient vector and all is going on all the time. And the machine learning methods have come in from computer science, so there is a lot of tinkering there in terms of the learning rate. What is also done sometime is that the factor xk here is multiplied by something called beta, that is called momentum, and so on. So again, the same type of methods moving around in the design space, but the approach is somewhat different. And remember, they are also trying to minimize a function, which is typically something to do with linking two data sets and essentially trying to minimize the difference between these data sets, or basically to find certain values of neural network parameters so that they can get a best fit on a function approximation problem. So anyway, I will end this topic here as far as gradient based methods are concerned, and we will then start moving on to the Newton type of methods where we are going to look at the Hessian matrix also, that is from tutorial 20.